So now we've seen the very basics of what a signal is, what bandwidth is, symbol rates, data rates, and we also learned that it's necessary to translate from the analog into the digital world and vice versa. Okay, we'll have now a bit deeper look into what is needed, quantization, sampling, and what is the maximum capacity of a physical channel. So coming back, we saw that we try to transmit, for example, an ideal square wave. So that's our intended ideal transmission. We already know it doesn't work this way because, well, you saw the examples. With the help of the sine wave, we can approximate this, we can come close, but not really to this perfect shape. So actually, we have to our physical medium will transmit this composition of sine and cosine waves following Fourier. Plus, we have a DC component in the transmission. So DC component, we'll see this several times. We don't like this. So DC freeness results in a signal that needs less energy to transmit, while maintaining the same error performance. So same signal to noise ratio. And the problem is this DC component doesn't transmit anything, any additional value, additional data. So the problem is that the energy we have to put into a signal is proportional to the square of the amplitude of the signal. And the DC component, as you see here, if we say this is now kind of a normalized amplitude, here as always a constant amplitude, and this wastes energy. So DC doesn't contribute to the signal, doesn't help, and so we don't like it. Plus, there are some technical problems with the DC component. If we, for example, couple different cables or technologies using transformers, we cannot transmit the DC part. But that's the basic idea. So we want to transmit this ideal signal, for example, and we know, okay, this is composed in real media on this sines and cosine waves plus the DC component. And the main problem, Claude Shannon already formulated this, the fundamental problem of communication consists in reproducing on one side exactly, or at least approximated, a message selected on the other side. So as the receiver doesn't know what the sender is sending, the receiver has to reconstruct the original message, or at least the receiver has to approximate this. So where are the limits? Okay, before we come to a formula, the famous formula by Shannon, we have to look again into analog and digital signals. So analog, typical analog signals, they are continuous in value and continuous in time. So that means at any given time here, for example, at this point in time, we can check, we can have a arbitrary value within a certain interval. And that's an interval out of R. So we can actually have any value of this interval. So no matter what you pick, so it's continuous. And also in time, there can be always a change in this value. So continuous in time and continuous in the values. So in our computers, we cannot store this continuous signal, so we cannot have all the numbers that are in R because it's infinite amount of numbers. So what one step we do is, first of all, we have to look at the signal at certain points in time. So we have the time now in discrete steps. So we check at t, for example, at 2t. So we check here in these certain intervals with fixed intervals. That's a typical way how you do it. And then we check the value and we stay with this value for the whole interval here. Then we check again the value. Okay, the value has changed and we stay with this value. So, and this is called sampling. We sample with a certain interval t in this case. So now we are discrete in time, because as you see, we sample only at a certain point and then we stay with this level of the signal. We can also look at our continuous analog signal, continuous in time and continuous in value, and say, okay, let's have only discrete values. So we allow only a discrete number of values within a certain interval. And so we pick something and we can even number them. So we can say, for example, this is 1 volts, 2 volts, 3 volts, 4 volts, or whatever unit we're looking at. So we can have discrete values. And to do so, we have to perform a step that's called quantization. So quantization will check a certain value and say, okay, we have to map this value out of a continuous interval onto a discrete value. So if you have a certain value, you have to check. There might be 2 discrete values and you have to decide, is it the value, the next discrete values that is larger or smaller than the current continuous value. So that's quantization. And if we do both sampling, discrete intervals, plus quantization, we have a digital signal. So continuous values, that's analog signal, and the digital signal now has at discrete times a discrete value. So that's the idea. So discrete in time and value. Sounds good, but if you compare those 2 curves, you see something that we created an error. And this is called quantization error. So if you perform this translation from the analog signal into a digital signal, you always introduce an error, the quantization error. Why? Well, again, you have this interval of our analog continuous values. That's an interval out of R. And then if we have a certain value, we have to map this onto our discrete values. And if you're somewhere in between, you have to decide, is it the value larger or smaller than the current value from R? So that's the problem, and that's exactly our quantization error. So it's impossible to create a digital signal that absolutely in all details reflects the analog signal. That's impossible, because you map something out of an infinite, an interval with an infinite number of values to a signal that has an interval with a finite number of values. So this is a quantization error. The other way around, it's not a problem, because, well, digital signal, then you can create the analog signal, but the analog signal then will only have certain discrete values. Okay, so from analog to digital, you always create an error. The question is the error, for example, if it comes to music, is it audible? For old, old analog systems, you could have all the values, but then the CD was introduced, MP3, etc. And it's all digital. And yes, they cannot 100% reproduce the original analog music. The question is, will you notice? If you do not notice, you do not care. Our today's world is fully digital, and we will not notice it. Because if you have many discrete signal levels, the human eye, the human ear is not able to distinguish, oh, is this discrete or is it continuous? Okay, we'll come back to this. So this is one important step, analog to digital. Sampling and quantization, those 2 concepts. Okay, the question is now, interval t. Who tells us how large should this interval be, or how small? There we can use the sampling theorem from Nyquist, and also Shannon and others also looked into this? Well, the point is, we learned already that if we have a signal, here shown the time domain, we can also look at the signal here in the frequency domain, and this gives us, well, at least the harmonics where most of the energy is. We know that sometimes maybe we have some more, but the majority here of the energy is somewhere here, and this determines our bandwidth. That's the bandwidth we have in our signal in Hertz. And the Nyquist, this sampling theorem, tells us if we want to reconstruct the original analog signal, it is sufficient that the sampling frequency is such that the sampling frequency is larger than 2 times this bandwidth. So Nyquist described this, Swedish electronic engineer, and some others, and this is really a fundamental theorem, and this tells us how often we have to look at the signal. So this is if we have our signal in the time domain, how often do we have to check the signal? Here shown by these dashed lines. And if we fulfill this, so it's larger than 2 times the bandwidth, then this is sufficient. And this is really the base of all this digital content, photos and videos and sound, etc. If it's not a baseband signal, I will come back to this baseband and broadband, then it's sufficient if it's larger or equal 2 times maximum minus minimum frequency. So if we look at a signal, now you have the frequency, and here we have the energy, signal strength, and then you go through the spectrum, and there might be something, and then we have the maturity of our signal somewhere here. We learned, okay, we have certain cutoff frequencies here, and then this is the effective bandwidth we are looking at. And then, so because this is here f max and f min, and then this is exactly the formula that our sampling larger or equal 2 times this bandwidth w here. That's sufficient. Okay, so the sampling theorem tells us how often we have to look at our signal. And if we follow this theorem, it's guaranteed that we can reconstruct the original analog signal. Well, yes, the point is we will ignore these higher frequencies, and the fact is that typically if there's not that much energy here, we don't need them to really get a signal that comes close to the analog signal and is sufficient for detecting our bits, because in the end we want to detect our bits. And it's similar to music. For example, if you use audio, we know that the human ear goes up to, let's say, 16,000 hertz. Then if we assume we have a cutoff at 20,000 hertz, then that's fine. So we can sample at 40 kilohertz, or in real systems it's even higher, so 48 kilohertz, 44 kilohertz, etc., which is sufficient, because we know there might be higher frequencies, but as we are no bats, so the human ear and has a certain limitation at 16,000, so we are no dogs and no bats, and so we can have a cutoff here. Okay, so how does this all come together? So we need, as a first step, this sampling. So sampling, we now know that sampling has to be done at least twice. Well, you take the bandwidth, if it's baseband, more than double the bandwidth, or if it's broadband, twice this effective bandwidth. This tells us how often we have to sample. So that's our sampling, the given rate. And then, if we know how often we sample, we check the value of the signal. That's step 2. So step 2 is the quantization, and then we check the value. Fine. So we check at certain times given by Nyquist, this theorem. Then we check the value here, and then we perform this mapping. We check, okay, if it's in between, I go to this lower value, higher value. This is where we introduce our error. We do not introduce the error when it comes to the sampling, if we follow Nyquist, but here we have the quantization error. Okay, and then additionally, as we will see in an example, step 3 is we have to code the result. So what does it mean? So for example, if this represents 3.3 volts, this will be coded as a certain code, for example. So that's step 3. So the quantization intervals, because you see this is a certain interval where I say, okay, everything that's within this interval, then we map it to a discrete value and we assign a binary code to this value. And then the idea is we only transmit the binary code. That's all we transmit. So we transmit the binary code, and if we follow these 3 steps and we follow the sampling theorem, then we can, at the receiver side, reconstruct the analog signal. So we have an analog to digital converter performing these 3 steps, and then we have a digital to analog converter performing the reverse. And we have to consider these independent steps. Sampling, that's from this continuous time to discrete time, and quantization, continuous value to discrete values. So we need these 3 steps. Okay, an example. So looking at this, now we have this nice sine wave here given. Let's assume we want to transmit this. That's an analog signal, obviously. So that's our analog signal, the original sine wave. And we sample this. So we see sampling shown here on the x-axis. Okay, we sample this, and then we go up at a certain point in time, and then we have to check the value, and we map then this continuous value on one of these, in this case 16 discrete values. So sampling, that's our step 1. Step 2, quantization. In this case, we have these 16 discrete intervals. And then we have to assign a code to these intervals. So that's the next step. So this is a quite concrete example from the very, very classical voice channel, analog voice channel. From the very early days of the telephone system, while the engineers looked at male voices in this case and said, okay, major energy of the male voice is somewhere between 300 and 3400 hertz. So we see here our F min, and this is our F max, and this results in a bandwidth of 3100 hertz. Okay, then we have to go at least to the double, so 6200. Okay, given the fact that maybe there are some low, maybe some bit higher frequencies, then let's go for a sampling rate of 8 kilohertz. Makes life simpler. That means we sample every 125 microseconds. So every 125 microseconds, we check the signal. And if we do so, we can, on the receiver side, reconstruct the original voice signal. Okay, so that's the idea. And then, so that's sampling. That's for our step 1. And then the step 2 is we use 256 quantization intervals, and we map this to a certain code. So that's the step 2, this quantization intervals. And if we do so, we generate every 125 microseconds 8 bits. We end up at 64 kilobit per second. And this was the classical ITU-T voice channel. At least for Europe and US, they had 56 kilobit per second. So 7 bits, etc. So a bit different coding. So we need for this step 3 we need a code for, and this is a quite straightforward code, code for the intervals. And then for each sample you take, you can generate this code. And all we transmit now is, now shown for these few examples, all we transmit now are these ones and the zeros. So that's the idea. And if we take all this together, we generate this 64 kilobit per second. And this 64 kilobit per second dominated for many, many years the whole digital phone systems. This guaranteed quite good voice quality. That was the base for ISDN, the digital telephone system. That is mostly replaced all over the planet now by voice over IP system, and due to better codecs, so coding and decoding, we can now go down to, depending on the codec, something around 12 kilobit per second, the classical cellular phone, etc. system going down to 5 and even 3 kilobit per second. But voice quality then, yeah, you will notice. So 64 kbit, that's quite a lot. 12 kbit, it's okay. But as we all know, cellular phone voice quality is not as good as the classical fixed line ISDN. But, well, it's understandable, so that's okay. So these are the 3 independent steps you have to perform: sampling, quantization, coding, and then you can transmit basically the bits. Just a remark, now we have ones and zeros. We cannot transmit ones and zeros, we know this, but what we can do now is we can actually transmit this digital signal. Now we are in a digital world and can do many more things like storing the voice and all these things. Okay. There are several more questions left open, like the digital channel. What is this? So digital channel doesn't exist. I told you this several times. That's abstract. So the real world, that's analog. Again, neglecting quantum physics, Planck's time, etc. So the question is, how much data, how many bits per second can we squeeze into these analog systems, analog channels? So what is the capacity of a channel? And can we calculate the capacity? Well, very simple. If the analog channel is noiseless, we have an infinite capacity in theory. Why? Well, remember, when we have our analog signal, we have all the values out of an interval from R, and okay, then we do this steps 1, 2, 3, and come in the end as a result with our bit stream. What we do is we code, we sample, quantize, and map this to these discrete intervals. So, but why not having more and more of these discrete intervals? So I cannot really draw this. Having more and more and more and more. Why not having an infinite or close to infinite? So many of these intervals. So we come even closer and closer and closer. In theory, that's possible. In real life, no. Infinite precision, so coding with an arbitrary size, is not possible because we have noise. So these intervals, I introduced this also already with this multi-level digital signals. So yes, it's nice to code this to certain whatever levels, but introducing more levels in between. So now we have, let's say here, these 3 levels. Yeah, we could have more levels, but as soon as we have noise added to our signal, and we see some examples for this, then maybe noise is that strong that suddenly you end up not at this value, which would be the correct one, but due to noise at the wrong value. So the smaller the gaps between these intervals are, the smaller the intervals are, the higher is the probability to code a wrong value. So in reality, you have the noise. And if the channel is noisy, you have a finite capacity. And this finite capacity depends now on many things like noise, for example. Noise, but also bandwidth limitations of the material. It's copper, it's fiber optics, so there's a lot. And noise, there are many sources for noise. And there's one typical classical model used for analysis of channels, AWGN. It's called also a Gaussian channel, and a German mathematician, Gauss. And here it's assumed that the noise is random, so random, independent, and with a so-called constant spectral density. So the noise is the same no matter what the frequency is, no matter where you are in the spectrum. If this is not always true for all the channels in real life, you can imagine that you have more noise where there are more senders. So at the frequencies of mobile phone systems, for example, there's more noise, etc. So that's the idea. And the amplitudes, there's also a certain distribution and so on. So, and the noise is additive, so the noise is added to the signal. We'll not go more into these more theoretical details. I will just show you what is the result, so the effect of noise. Assume we have data, okay? That's what we think of, that's what we store, but data has to be represented, a signal. Now we try to transmit this nice digital signal over a line. Then we have noise shown here. This noise will now overlap, add to the original signal, resulting in a signal including noise. Now we have to start sampling. Hopefully we sample at the correct times. That's a question of synchronization. And we sample and check, okay, so maybe we check exactly here. Then this should be a 0. So everything that is below the threshold, assume to be a 0. If it's above, we assume this is a 1. So we sample this, and then we, check if it's below, then we assume this was a 0. If it's above, we assume it's a 1. If we now compare this, we will see, okay, that's our original data. Oops, we have errors. So depending on the noise, in this case, we have original data 0, but strong noise, creating something that's above the threshold, interpreted then as a 1. And here, the interference kills this bit. You see here, and then this then results in a 0, which is also an error. So it might happen that you flip single bits or several bits. That's quite common. So noise can create errors. And the error-free channel, well, in theory, yes. In real life, no. So all the physical channels, they all have interference, they all have thermal noise and all the just the question is, how large is this compared to our signal? So what is the effect of noise? Well, in analog signals, you degrade the signal quality. So because, you have the original nice signal, nice music, whatever, and then there are cracks and whatever on your LP, and then it's more maybe like this, whatever. And then it's the question if you hear this or not. And some people even like it. And digital signals, discrete times, discrete values, noise may cause, actually bits to flip, and depending on the type of the noise, etc. And then suddenly you have flip bits or even bursts of flip bits. So you cause bit errors. Yes, you can diminish the effect of noise by boosting signal amplitudes, make the real signal stronger compared to noise. So that means real strong signals, but that's a lot of energy you will need for this to make a strong signal. And if you have strong signals, you as a sender cause more interference, especially in wireless. So it's not a good idea to have a very, very strong sender, because then all the others would say, oh, this is sending quite strong, so I also have to send strong. That's like in a party when one person starts speaking louder and louder and louder, you also have to speak louder and louder. In the end, everyone is shouting. So a lot of noise, loud noise in this case. So what happens? Noise, thermal noise, crosstalk. So crosstalk, that's something quite common in wires. That means you have one wire going this way, another wire going this way, etc. And so many wires. And if there's a certain current on the wire, you know from physics, you create a magnetic field around the wire, and this can couple into the other wire and then also generate a current there. So crosstalking. And many more. Then there are some other ways of distorting signals, so attenuation. So we will learn that if a signal goes through fiber or wire or whatever, you have attenuation, so the signal gets weaker. And the problem is not all components of the signal experience the same attenuation. So some frequencies are attenuated more, some others less. There's also delay distortion. So I mentioned this already in the context of fiber optics, that some wavelengths are faster and some others are slower because we are not in vacuum in space. Okay, so how does this in the end affect our data rate? Because we are from computer science, we are interested in data rate. So first of all, we learned that, okay, noise and all these effects, they can cause bit errors. So what is an important number for us is the bit error rate. Bit error rate is just the relation of how many flipped bits do we have compared to the number of transmitted bits. And this depends on the environment, this depends on the medium, the length of the transmission line. So you can imagine the longer the line is, the more bit errors you will have, because there's more chances to have interference. We have effects like problems of high frequencies, attenuated much stronger compared to low frequencies. And you have these effects of this dispersion, different speed in the medium. And so there are typical values. So for example, classical fiber optics, so it's only very few bits. As you can see, the bit error rate is quite low compared to radio links, so wireless LAN, for example, with very high bit error rates. And this is why we need certain mechanisms to counteract this. And you will learn some of them. So we have bit errors, okay, in real channels. But is there a formula? What is the upper limit? How many bits can I transmit? Well, can I go to infinity? Yes, if you have a noise-free transmission system. But in real life, this doesn't exist. And there's, I would say, one of the most significant master theses of all times by Shannon, also called father of information theory. He assumed a certain channel, the Gaussian channel. I told you about this one. And Shannon came up with a theorem saying, okay, the maximum data rate we can get out of a channel is the bandwidth in hertz of the channel. So that's our bandwidth here. And bandwidth, we know that typically all media, they have certain characteristics. If we look at the attenuation and on the y-axis and the frequency, then typically some of the medium, for example, fiber optics, you cannot transmit anything with too low frequencies. And then there's a certain window, that means certain colors, certain frequencies fiber optics can transmit. And well, will be high attenuation. For example, you cannot transmit X-rays over fiber channels. So there's a certain bandwidth you can use, and that's this W. And this is true for all real media. Some media, They have characteristics like they start already here at 0 with very low attenuation, and then they go up. So copper wire, for example, and then you can only use this part here. For fiber optics, somewhere else. Okay, so this is the bandwidth. Bandwidth times log of 1 plus, and now we have the so-called signal to noise ratio. What does it mean? That's basically the ratio between how strong is the signal that carries your data in the end compared to the noise, average noise around us. And you see already from this formula what happens if you have no noise, or at least very low noise. If this goes to 0, the whole term goes to infinity. Because, well, you divide 0, etc. Not really by 0, but something close to 0 goes to infinity. Logarithm of almost infinite is also almost infinite. So, infinite data rate. Okay, so, but Shannon limits our data rate. No matter what you do, you cannot go simply assuming these channel conditions, etc. You cannot simply go beyond. Oh, what happens if you go beyond? Yes, you can. You can try to transmit more bits per second over the channel. If the channel has these limitations, you will create more and more bit errors. So there are several schemes that try to go beyond because the conditions of the Gaussian channels are not always true, because noise might be different, so you do not always have this Gaussian channel. This is just, well, one very fundamental theorem that helps a lot, because if you apply then some simple numerical examples, if you say, okay, our channel has this 3000 hertz, for example, channel width, or 3100 for a telephone line, a certain signal to noise ratio given, then you can do the math and say, okay, max data rate is something like, in this case, there's whatever, 30 kilobit per second. So this is one way of calculating the upper limit under certain conditions. So independent, identically distributed, noise, etc., Gaussian channel. So now we can also bring this together with Nyquist. So if we do not consider noise, what is then the upper limit? Well, it's the quantization and the sampling. We know we need this sampling at a certain rate, and we need quantization to create the discrete levels of the signal. And Nyquist also gave us the max throughput depending on the number of discrete signal levels, telling that, okay, the maximum data rate is 2 times the bandwidth of the signal times log of discrete signal levels. So this is basically complementing Shannon. So Shannon gives you an upper bound for the data rate for a channel with noise, telling you, okay, that's the upper limit. You cannot go beyond this. And Nyquist tells you what's the maximum data rate depending on here the number of discrete levels of a signal. If we only look at this Nyquist theorem, remember, why not having more and more coming closer to infinite number of discrete levels? Fine in a noiseless channel, but you cannot really implement this because all the channels have noise. But at least you see you have a certain max data rate depending on these levels if you follow Nyquist. So how does this help? So if you have a channel and Shannon tells you, okay, this is the limit. Then if you look at a concrete coding and you see, okay, Nyquist is lower than Shannon, then we can actually have more and more levels, discrete levels in this signal. We can go closer, coming closer to this Shannon limit. If we go beyond, then, okay, you can do this, but you introduce a lot of errors. There are ways of doing this, so you can do this, but you integrate what we call forward error correction, and you can correct the errors, but that's more signal theory. So for us, it's important to see, okay, if we are far below the Shannon limit, then let's go up and let's use some more signal levels. We should not really cross the Shannon border. We can, but that's something different. So Shannon and Nyquist, they both go together, and we have to look at both to see what's going on. What is the upper limit, for example? Some questions. So why? Go back to analog to digital conversion. Why is this not lossless? In theory and for real systems, what's the difference there? And is this a problem? So maybe there are losses, but who cares? So maybe why can we say we don't care? So what happens if we saw there's this Shannon limit? What happens if we go beyond this, assuming certain types of channels? On the other hand, what happens if we sample too often? We learned, okay, what is at least required for sampling, but what happens if we do more oversampling, so more samples than necessary? Is this a problem or not? What happens if we use more and more discrete signals for quantization? We can do this, but there might be a problem. And then looking at the Shannon and Nyquist, there's always a question, so this theory, how many bits per second can you transmit over a noiseless channel? Nice, but why is this answer basically useless?